Yeah, good. Good morning, Rain. Hi, Anna. Anna, you should look at the whiteboard. I put a message for you there. So, thanks everyone for sending in the project proposals. That was really helpful. I tried to give a quick feedback, and so everyone should have that in their Canvas folder now. I think everybody is well on track to having a good piece to do for the final bit, and so all we have left is that and this last homework, and we're good to go. So please do follow up with any more questions you have via email. I realize that there are lots of significant complications, and things are probably not going to turn out as well as we might have hoped, or and there are lots of unexpected difficulties. Things are just harder now than they have been before. I will admit that I've been trying to use a rowing machine to keep myself feeling a little bit more calm, and this morning I could only do half as much time as I wanted to do. So I know everyone's energy level and enthusiasm is lagging. So, but be sure that I have that in mind as well when we're thinking about how we're doing all this. And the main thing here is to try and learn something so that we have gained some skills that'll be useful after all this stuff is over. So, any questions about anything on the homework or anything else before we start? Oh, so you could click over onto the other presentation and you'll see the whiteboard. The other version of me. And do you see the message? Everyone else can look over there too. It just says good afternoon in Italian. I figured we've been saying good morning every day. I thought it was time we mix it up. Okay. So, so last time we closed on this concept of what happens when you get. So last time we were talking about the surface layer, which is this layer where basically the U star scaling dominates everything. And there's a constant flux condition across that layer. So the boundary conditions on U star set the scaling, the stresses like U times W on average, scales like U star squared, and the effects of convection, either stable or unstable stratification from warming or cooling at the surface, are relatively modest. So at the end, last time, we closed on this idea: what happens if you're either under weak stress conditions or strong convection, or generally you're just in this regime where you've gotten for unstable stratification, we're minus Z over L, which is a positive number because in convective forcing, L would be negative. If that's much bigger than 1, we could get there either by thinking about it as the weak stress condition, the strong convection forcing, strong warming at the surface, or generally just being higher in the atmosphere than 0.1 roughly minus Z over L. And we talked about the fact that in that limit, it should eventually become independent of the stress to some extent, to a less extent, and so that linked us to a couple of predictions of what the RMS vertical velocity would be, which comes out to be a scaling that doesn't depend on U star. So if you plug in this and you plug in what the definition of L is here, since L goes like U star cubed, this side goes like 1 over U star, this side goes like 1 over U star. So the U star cancels on both sides. And so the RMS, the root mean square vertical velocity, goes like something that's not a function of U star. It just goes like the cube root of the surface heating. Similarly, the RMS temperature variations, which should go like T star, but T star goes like Q on U star. You go through this exercise and find that this ratio with the minus 1/3 power is independent of U star. So the idea that there might be a possible balance above the stress layer that doesn't depend so strictly on U star but depends on something else is sort of seeded in our minds. We're going to talk about that limit today, and then on Wednesday we're going to talk about the opposite limit, which is when we have strong stabilizing buoyancy forcing plus weak stresses. Again, in the limit of Z over L, but now L is a positive thing, so when Z over L is positive, we find a different set of conditions which are given by these, where now this stability function is proportional to Z over L, is what the limit is, because everything else becomes constant in this side of the equation. So we will come back to that on Wednesday. So if we are above the surface layer, so the surface layer, remember, is where minus Z over L or plus Z over L, the absolute value of Z over L is less than about 0.1. Above that surface layer, what happens? So under convective forcing, there is another boundary layer called the convective boundary layer. So let's remember how that looks. So there's a surface layer where there's shear in the velocity profile that has lots of interactions with the surface. That's where the law of the wall might be relevant. That's if you were really close to the layer. If you're up, you could have a combination of maybe convective and stress forcing when your Richardson numbers are kind of modest. And then up here, you have these above, you have these convective plumes. There might be clouds. There is a boundary layer depth that you might bang into if you have this convection go deep enough as to hit the upper layer of this. So that's what we want to talk about today. So kind of to put the answer at the beginning, this is the kind of profile that we're going to expect to see. So the surface layer, where absolute value of Z over L is less than about 0.1, is down here at the surface. And in that layer, we expect there to be some gradients in temperature between the warming surface and above. There are also some gradients in other passive scalars, if you like. And we know there are going to be gradients in both components of velocity. But above that, we have these turbulent plumes that are zooming upwards, banging into the stratification above, this capping inversion that we've talked about a few times. And maybe there's some transition layer in between those plumes and that stratified layer. So this interfacial layer is the interface between the mixed layer, that is the part that's vertically well mixed in temperature because of those convective plumes, and the layer above. In order to have a mixed layer like this, you tend to have approximately linear profile in the vertical transport of heat. And why that's the case is because if you think of the divergence of the temperature, virtual temperature, if you could take ddz of it and end up with something that was other than a constant, it would tend to accumulate temperature at that level. But since this is a well-mixed layer, tending to be pretty homogeneous in temperature, the way that you preserve a homogeneous temperature, maybe the whole thing is warming up or cooling off together, but it tends not to have any anomalies in the temperature flux divergence within that layer. And that's why you would think that there would be a linear profile that would be matched to that. In tracer, a passive tracer, we're going to talk about this at the end. We have a little bit more of a complicated situation, but you can imagine that there might be some modest gradients in the passive tracer where there weren't ones in the temperature. We're going to see why that is when we get to the end and we talk about the top-down and bottom-up tracer concept. If we go back to the Monod-Nabokov similarity theory, where remember we had the length scale of the turbulence, which was taken as distance from the surface, the velocity scale of the turbulence taken as the friction velocity, the square root of the magnitude of the mean kinematic surface stress, which is what the friction velocity is defined as, the mean temperature flux of the surface, Q naught, and the mean conservative tracer at the surface, and the buoyancy parameter. If we put those together, remember that was what gave us the Monod-Nabokov theory for the surface layer. But if we have this structure where somewhere up above there is a return to a higher stratification, that is actually another parameter, this Zi, which is the height of that interfacial layer. So if we add another parameter in, then we have the option of having a new dimensionless parameter, which looks like this. It's Zi over L, and so it also scales with, this is written in such a way as to be a velocity scale, W star, so W star over U star is 0.7 times Zi over L. Zi is this height again, L is the Monod-Nabokov length. So let's think about what that says. If this is a big, big number, it says that Zi is much, much higher than the Monod-Nabokov scale, which means that there's plenty of room in this mixed layer beyond the Monod-Nabokov depth or height. When there's plenty of room, we expect there to be really vigorous vertical velocities because of the convective forcing. And notice also that there's a minus sign. So minus sign, remember, is when the Monod-Nabokov is an unstable boundary layer. So we have minus sign here, positive Zi. That's giving us a big number, which says that this W star is much, much bigger than U star. So, in fact, this is a good scaling for the convective velocity scale, which is usually written as W star. You can think of it as the vertical velocity that results from the buoyancy forcing, and the same way that you can think of U star as a horizontal velocity scale that results from the surface stress. But since this is isotropic turbulence, or relatively isotropic turbulence, both within the surface layer and within the convective mixed layer, you could also think of W star as being a horizontal velocity scale for the part of the plume that connects at the top. And U star could be either the horizontal velocity or the vertical velocity within the surface layer, either one, because it's relatively isotropic turbulence, within an order of magnitude being isotropic. Okay, so that's the conception we have. We have this mixed layer. We have a uniform, linearly decreasing surface flux, and we have a nearly uniform passive tracer, a more complicated passive tracer flux that we'll talk about in a little bit. So one of the things you might get very suspicious of is, remember back to our idea of eddy diffusivity? So what does the eddy diffusivity say about this theta W term? It would say that theta W is proportional to the gradient in mean theta. But there is no gradient in mean theta. It's just constant. So we can already see that there's something funny when we think about this as an eddy diffusivity layer. We'll come back to that at the end. It's that idea of there being a simple similarity theory by just adding in this extra parameter doesn't really work very well. There's some more complexity, and Wyngaard goes into great detail about the more complexity that you have to think about, because really the convective layer isn't as independent of the surface layer properties as you might think. So without going into a whole lot of detail, I just want to put that in your mind that this is already showing that similarity theory is of limited applicability. That second piece that I just talked about, whether there's an eddy diffusivity meaningfully or not, that part will also come back to. But I think that's an important distinction of the convective layer as well. So what about the stresses in the convective boundary layer? How does it work? Well, if we take the Reynolds stress budget, actually it's the TKE budget because it's the same component of the Reynolds stress, we have a shear production term, we have a transport or triple product term, we have the pressure term, we have the buoyancy production or buoyancy destruction term, buoyancy production term, and the convective version, and then dissipation. And you can see that if we look up, so here's the surface layer down here where the shear production term is large. Above that, the buoyancy production term is large, and it's basically balanced by dissipation, with a little bit of this transport term that's grabbing some stuff from down here where the shear production is and depositing it up here so that the buoyancy plus the triple product add up to essentially epsilon. So looking down here, we have and a little bit of the pressure term too. T plus P, these two terms are giving us the excess that goes beyond buoyancy to match with the epsilon. So the important piece of this story is that buoyancy is involved, dissipation is involved for sure. That we would have guessed right off the bat. But these transport terms are also important, where the surface layer is linked to the convective layer. And that's probably why the similarity theory of the limit where the surface layer is totally disconnected and the upper layer is just a convective forcing probably makes sense. That kind of assumption would tend to have the buoyancy production equal to the turbulent production. The turbulent dissipation. What about the shears that we expect to get in this layer? So we can go back to our steady momentum balance for the along wind surface wind component and the cross surface wind component. And we have a three-way balance between the Coriolis force on the flow, the pressure gradients, so the baroclinicity term, and then the Reynolds stresses, the divergence of the Reynolds stresses. Or if we write the pressure gradients in terms of the geostrophic velocity they imply, that really isn't the geostrophic velocity that's seen within the boundary layer. That's not the velocity, that just says that what the Reynolds stresses do is they make the boundary layer velocity deviate from the geostrophic value up above the convective boundary layer where this term is small. We expect to have the velocity equal to the geostrophic velocity. But within the boundary layer, we expect there to be a deviation from the geostrophic velocity. So interestingly, we're going to talk about this more, but this is actually a very hot topic, this kind of conception for how the momentum balance of the boundary layer works in the ocean, which the idea is that the deviations from geostrophy had to do with the turbulent momentum stresses. And we'll see how that causes frontogenesis and lots of other things to happen in the ocean when we get back to the ocean. But for now, I just wanted to point that out. If we take the z derivative of this, of these two balances, we get the z derivative. The f doesn't vary in the vertical, so we get the z derivative of the velocity in the boundary layer, the z derivative of the geostrophic velocity. But the z derivative of the geostrophic velocity we already know something about because we know in hydrostatic geostrophic balance, which is appropriate for the mean velocities, even if it's not appropriate for the turbulent velocities, then the ddz of the geostrophic velocity is related to the horizontal gradients of temperature. So the thermal wind balance is this balance just between the shear and the velocity and the horizontal temperature gradient. It could be in either the u direction or in the v direction. A deviation of that caused by the divergence of the second derivative of the Reynolds stresses is called the turbulent thermal wind balance. So this is a three-way balance between the deviations of Reynolds stresses from constant, the curvature in the Reynolds stresses, versus the balance between the pressure gradients forced by temperature, or really it's the horizontal derivatives and the vertical derivatives of the pressure gradients balanced by the vertical shear of the Coriolis force. So you might wonder, this is kind of elaborate, and there are two derivatives down here. That's going to make diagnosing this effect very noisy, and you are right. In fact, it does. We'll see in a second that this is very hard to diagnose from observations. This balance does happen quite naturally in models, particularly models where the turbulent stresses are parametrized, so that the averaging operator is replaced by a kind of most likely value rather than sampling from a very noisy turbulent distribution of Reynolds stresses. Okay, so, but what if we neglect the thermal wind? What if there's no horizontal temperature gradients? Then what do we get? Well, we get the stress is just balancing. There is no VG in that case and no UG in this case. So the DDZ of the stresses is giving you the flow within the boundary layer. And so you can, and this comes with some limits, because if that's the case, then by the time you get up here above the boundary layer, you have actually reached a geostrophic velocity, even though that geostrophic velocity is related to temperature gradients, but if there are no temperature gradients locally, then there's no shear in the geostrophic velocity, so the geostrophic velocity is just a constant up above. And in fact, the only way this can really work out is if that geostrophic velocity up above is matched to both the boundary layer depth and the surface stresses in such a way that this kind of a balance holds. So let me show you what I mean here. So here's that geostrophic value aloft. Here's 0. So we expect in this direction, which is the crosswind direction, to have no velocity throughout the boundary layer, and then a jump in shear to jump up to that value up above the boundary layer. That goes with a steadily increasing and then suddenly decreasing amount of stress, which is basically a small enough amount that there can't be a second derivative in this, because if there was, it would start driving flow down here. So this is about as complicated as you could expect to get. You can show that this part goes with something called WE, which we're going to talk about in a little bit. This is the rate of entrainment of moving air aloft. So this air is moving aloft because of this. The air above the boundary layer has to be moving because of this balance that we already talked about. This one says if you had some entrainment, that is, if you were gobbling up free air above and bringing it into the boundary layer, it could lead to an acceleration. And so we'll see where that comes from in a little bit. In the wind stress direction, we have no wind right at the surface. Then there's a surface layer, and then throughout the rest of the boundary layer above the surface layer, you expect to have basically a relatively constant flow in the along wind direction that is aligned with the geostrophic velocity above the boundary layer. So notice that above the boundary layer, the geostrophic velocity is not going in the same direction as the surface winds. There is always a tilt between these two, which is set by the magnitude of this component versus the magnitude of which depends on the depth of the boundary layer, the Coriolis parameter, and the amount of surface stress. And again, you don't have any divergence in the stresses, the turbulent stresses in the along wind direction either. They just drop down linearly toward the boundary layer depth. So that's the balance that we expect in a barotropic convective boundary layer. Relatively simple. Yeah. Sort of. Ming-Shi just asked if we needed to assume whether U star is much, much less than the geostrophic velocity. We do in the sense that we have to have a mixed layer that is taller than the surface layer. So I believe that comes naturally out of this scaling through the balance of U star over FZI. Essentially, VG over U star over here, VG over U star goes like U star over FZI. So that you don't have to assume, or I guess you do have to assume that ZI is bigger than L or minus L in order to get that balance to work, because you need to have a convective layer above the stress layer, if that makes sense. So this, you have that. Does that make sense? You're integrating from this surface term, the surface set of equations. Okay. Which term are you? You're neglecting the integral. This term, this VW can't be big, right? I think so. You get a surface condition on this VW term in this part of the equation. And yes, that does have to be small. So if you had an enormous amount of entrainment at the upper surface, so that there was a large VW bringing down momentum from above into the boundary layer, then you can't get this balance to work. That has to be asymptotic. That has to be small, so that the du dz is relatively small as you enter into the interfacial layer for this balance to work. But that's not quite the same as U star being less than VG, because it depends on the VG is here. It depends a little bit on this, on how you match the boundary condition at the top of the boundary layer, I think. Oh, so they are constrained in that you have the one is the direction of the surface wind, and one is the component not in that direction. So the component not in the direction of the surface wind is constrained, but you can try and puzzle around what's the way that you actually think about how this is all constrained. It's, remember, so these two terms, the turbulent thermal wind vanishing, the thermal wind pieces are really talking about the ddz of the geostrophic velocity rather than the magnitude of the geostrophic velocity. So we still have some geostrophic velocity above the boundary layer in both cases. There is a VG component, there's a UG component. But you don't know what UG is and what VG is. You don't know which one is in the direction of the boundary layer and which one is perpendicular to that until you satisfy this scaling law right here. So it's the veering, the turning angle as you come to the top is set by how big this term ends up being once you plugged in the stresses and then figured out how much it veers. Does that make sense? You can think of the geostrophic velocity above the boundary layer as being a fixed quantity and go backwards and work out how much the surface velocity deviates from that geostrophic velocity aloft. Okay. All right. Very good. Thanks. Okay. So as we were saying, you might expect this to be extremely noisy because there's so many derivatives here in this turbulent thermal wind balance, especially if VW was really turbulent, and so VW bar was kind of a noisy average over something like this. And up here in the convective boundary layer, we'd expect that V and W would scale not with U star, but with W star, which could be much, much bigger than the imbalances on this side of the equation, than the imbalance that it causes. So there's a lot of noise. There's a lot of averaging that you'd have to do to get this sorted. Wyngaard spends an awful lot of time talking about how difficult this balance is to observe. Here's maybe the key figure for that, where he plots U and UG and V and VG, both scaled by U star, across the convective layer. So here's Z over ZI. So here's the top of the layer up here. And then down here somewhere is the surface layer. It doesn't tell us exactly what L is, but you can guess that it is from the shape of U to be down here somewhere. So look at this equation up here. It's V minus VG. So that's V minus VG. So here VG is positive and V is a little bit smaller. So this is negative. So du dz of uw is supposed to be negative up here. So we go to u, z. Oh, wait, sorry. Am I looking at the right one? V, VG. Sorry, I got to get this back right. V minus VG. If VG is bigger than V, VG is that they're fitting this to. But this part of the negative slope is sort of indicating that. Kind of. And on this, looking at this equation, VW, what's the slope of VW with Z is kind of positive and kind of negative. And so if we look over here, that's if UG is bigger than U, and it looks like UG is slightly smaller than U. So this side is negative, so this is kind of a negative slope. But you can see that basically it's not a very clean fit. Not only because the surface layer balance is, but essentially this transition from positive slope here to negative slope here, or positive values to negative values in these quantities doesn't cleanly line up with the relative ratio of these two over here, and it's basically, you can kind of get a sense that there's some relationship between them, but Wyngaard says that essentially this is because you're not able to observe this balance long enough that you can totally eliminate the other effects, either of baroclinicity within the boundary layer, which we would have had, I guess you could have baroclinicity in the boundary layer. Sorry, that's not disallowed here. Baroclinicity in the boundary layer would change VG without changing U. So you have kind of multiple competing effects on that front. But in addition, you also have a big DDT, which is that there could be a rate of change of these. So these could be accelerating. And in this particular set of snapshots of observations, whether these are perfectly balanced or whether there's some residual time scale left over is hard to figure out. So that leaves us a little bit puzzled as to how to observe this. Yeah, I think the solid lines are supposed to be a theoretical prediction. Oh gosh. I didn't go back to the paper, to the Lin Chao paper to read it, but I think actually Lin Chao is an LES paper. And so I think that that's a model fit to the same conditions as the observations were collected, but the observations are just those scattered points, if I understood correctly. Yeah, and not only that, but the lines don't seem to agree with the equation 11.6 either. So it's not just a theory, it's not just the integral of the equation above, it's something more complicated than that. So I think it is an LES. So the LES is also not in total steady state to the point where this is a clean relationship. But But like I said before, if this was a parameterized UW bar and a parameterized VW bar, then you might actually expect something like this to come into balance pretty cleanly. Because if it was parameterized, then the anomalies of the space or time accumulation, you could handle them explicitly. So we'll come back to that in a little bit. So, but one thing that I wanted to point out before we move off of this topic is, so a baroclinic convective boundary layer has a convective boundary layer, so it is a mixed layer. It's mixed in the vertical temperatures, but it's not necessarily mixed in the horizontal temperatures. So if you remember this figure, it shows a boundary layer that's coming and going, up and down, but look at all of the horizontal gradients that are also there. So even though there's not much gradient in the vertical, except for that height of the boundary layer, there's plenty of gradients in the horizontal. We'll see that that's true in the ocean as well. So a baroclinicity is not the exception to the barotropic rule. It is much more the case that most boundary layers have some baroclinicity. So we'll think about what that means, particularly when we come to the submesoscale in the ocean. Okay, so returning to that concept of eddy diffusivity, remember we said that in this schematic, it's hard to imagine how, not that schematic. In this schematic, it's hard to imagine how you have a flux with no gradient. So you can't really have a diffusivity to explain that. So Wyngaard goes into quite a lot of detail to think about this. In the surface layer, where you have gradients in du dz and gradients in dv dz, you certainly can make this relationship and come up with a profile of the km, and it goes kind of like this. And so this is a way of measuring km within the surface layer. This whole game seems to work because the presence of the surface means that you're always kind of, velocities are changing a lot from zero at the no slip condition right at the surface up to something aloft. And so across that layer, the eddy viscosity is doing something. You can at least make this ratio and say, and that you don't expect the udz to go to zero. But if you try and do the same thing for within the convective boundary layer, or within the convective boundary layer kind of breaks down because the gradients are really decreasing. If we go back and look at our idealized one, and we didn't have any gradients in temperature, but we also, where did the other figure go? We also don't have enormous gradients in velocity. So it starts to become really complicated and sort of it doesn't seem to be a very good description to think of a flux gradient relationship in the convective boundary layer. In some of the theoretical approaches, you could have a limit in which you can predict what that scaling is supposed to go like, and but this is extremely hard to observe. And so Wyngaard goes through this again and points out that basically this is a big and noisy term over another big and noisy term. You could assume this kind of a scaling which is consistent with that, where W star Zi, so basically the vertical velocity of the convective layer times the height of the convective layer, scales with that gives you your diffusivity. And so you could think about something like this and you could try and measure this, but it doesn't really work very well because this gradient is so small that you're looking for something that's a ratio that you want to be 1, but it's close, but this numerator is extremely noisy and this thing is very small. So essentially, this is not a very well posed linear problem. And so any deviations from this eddy diffusivity theory would be hard to detect, and the eddy diffusivity itself would also be hard to detect. But nonetheless, this is still the basis for a lot of closures for Km, where you might say that there was some vertical velocity scale, the boundary layer depth scale, or not the boundary layer depth, the mixed layer depth scale, you multiply those two together and you set that proportional to the diffusivity you get. And that's essentially this balance over here, which is showing the scaling of that versus that. Okay, so I'm not going to focus on this part of it. You can go into the stress budgets of the convective boundary layer and try and make sense of it. It's not terribly easy, but I want to talk instead about passive tracers, which is the last piece. The main theme of the convective baroclinic boundary layer is that it's hard to get statistical significance in the observations. Okay, but the last piece that I wanted to talk about is, oh, did I have that? No, I don't. Is this idea of top down and bottom up. Oh, let me see. Can people still see that? Could people still see this slide? Maybe I better not do it. Here, I'll show you this way. I'll do it this old-fashioned way. So imagine we had a convective boundary layer and we were releasing tracers at the bottom level. So, I don't know. Maybe carbon was being released from the surface. So we're supposed to be imagining passive tracers here, not active tracers. So not tracers that affect the velocity, just things that are carried around by the velocity. We might expect those tracers to have some profile like this, where the surface is the source and it's decaying, and over time you're kind of filling out more and greater concentrations, but since the source is at the bottom, you fill in this boundary layer from the bottom up to the top. Alternatively, you could think about having a source aloft. I don't know, aerosols or, nitrogen isotopes or something that was coming over a region where it was an anomalous from what was in the boundary layer, and then you might imagine in time it would be propagating its way down. So if we think about it from the perspective of the tracer equation, the rate of change of the concentration within the boundary layer is really just a function of the turbulent transport from the surface or the upper interface of the boundary layer into the boundary layer. And so that you could either have it provided from the bottom and going up, or provided from the top and going down. And you can actually write this out formally because this equation is linear in the tracer concentration. So you can pretend that there were actually two different tracers, one that comes only from the bottom and one that comes only from the surface, and you add them together like this, and then you get the total being a linear combination of the bottom up and the top down tracers. So imagine, let me say that again. Because this is a linear equation in the concentration, you could take it as the superposition of two different tracers. One which was the source of that tracer coming from the top and going down, and one that was the source at the bottom coming up. The other boundary condition would be zero source for the top down one from the bottom surface, and zero source for the bottom up one coming down from the top surface. If that makes sense. If you added those together, then mathematically, because this is an equation that's linear in tracer concentration, you would get the total tracer concentration as being the top down part, or bottom up part plus the top down part, and it looks something like this. So the interesting thing about this is that this is predicting symmetries that you would have in between this top down and bottom up part. In particular, if you flip this boundary layer, so if I took the top down one and flip it upside down and then flip it the other way, so that I can compare it between this profile and this profile, I would expect that over time it would look just like the bottom up one. The top down one is kind of an upside down version of the bottom up one. That's only true if the way that the turbulence is mixing through the boundary layer is kind of symmetric from the top of the layer down and the bottom of the layer up. we can push this analogy a little harder and try and write the top-down tracer equation, something like this, and use now the Monod-Nabokov similarity, the extended Monod-Nabokov similarity, to come up with a scaling that looks like this. And here's the extended Monod-Nabokov similarity for the bottom-up tracer, which looks something like this. And so if there was going to be symmetry between the top-down and the bottom-up, then this GT, this is just a dimensional analysis, essentially, at this stage. So the big question is whether the shape function, the shape from the top down and the shape of the bottom up, are they symmetric? Are they just the exchange of each other around some center value of z halfway between 0 and zi? It might not be exactly halfway, but you can imagine asking whether they're symmetric. And so down here again, I've played the same game. Here is a measurement of GB from an LES, and this is a GT. So the top-down shape function looks like this, which is essentially the shape of like a diffusivity. It propagates, it's decreasing, and then the bottom-up looks like this. And you can see that for part of the profile out here, they're pretty similar. But for this part, there's something really, really different about the bottom-up tracer. In fact, it crosses through 0 right here. This thing goes to 0, which means that there is a singularity in the bottom-up tracer. So if I flip it upside down, same way as I did before, this does not look like that. They're not symmetrical. And crossing through 0 means something pretty substantial. It means that you can't use a diffusivity to talk about how this tracer propagates. You can go into the higher order and try and do the equivalent of the Reynolds stress budgets, but now for the tracer transport coming from the top and the tracer transport coming from the bottom, and you can look at these things. Oops, let me remove that for now. So here's the bottom up, and here's the top down, and you can see, just by eye, you can see that, look, the B term here is really pretty different. The covariance of temperature and tracer is really, really different for the top down and the bottom up tracer. So if I flip that one upside down, you see that it doesn't look anything like this. And in fact, the M term here, this kind of variance, the thing that's the equivalent of the shear production term of the tracer, is really, really different between these two runs, actually have different signs. So the lesson learned here, the way to think about this is the descending plumes are very different from the ascending plumes. And so the covariance of tracers that are released at the bottom of the layer and go upward are very different statistics from tracers that are released at the top of the layer and brought downward. So you don't get symmetry between those two. And the bottom-up tracers, in fact, tend to have this singularity, which means that they're like behaving in a way where they're being released from the bottom and they're proceeding through the layer in a way that's unlike the mixing downward of the top of the upward layers. And so this has to do with the statistics of essentially buoyant plumes co-varying with the tracer concentration released from the bottom-up case. So if this did work, that there was a top-down and a bottom-up part, you might want to revisit the ABL scaling for the convective boundary layer by adding now the bottom-up flux of a scalar, but also the top-down flux in your similarity theory. That's one consequence of this. But another consequence is, we talked about this in the context of temperature, but this would be equally true for the tracer, for the concentration gradients, that you might have an eddy diffusivity that might work in the surface layer, but up above in the convective layer, you need to specify something else. So that the vertical transport of temperature or the vertical transport of tracer has a diffusive part, and this other object, which is called the non-local flux. So this is a flux of temperature or a flux of tracer that doesn't depend on the local gradient. And the reason why we need that, remember, is because we were seeing transport through a layer where there was no local gradient. So some of this transport seems to care more about the average over the whole layer or the surface flux, but not the intermediate gradients. So a diffusive closure is not a clean way of writing this. So Deardorff put this form into place, and when we talk about KPP next week, the K profile parameterization, we'll see that it actually uses this in a prognostic boundary layer equation. Okay. The last little bit of conversation is to think about what's going on at the surface. So if we have this top-down tracer, and we also talked a little bit in the momentum equation about the entrainment velocity at the top. So how does that work? Well, basically, if you have these plumes that are going up across the mixed layer and banging into the interfacial layer, they're going to start entraining air from above. They will occasionally penetrate through or penetrate up to the top of the interfacial layer, grab some air from up there and bring them back down as they're returning. Or alternatively, the air from above might drop into a low spot in the instantaneous location of the upper boundary layer, and then maybe there's an overturn, and then that gets entrapped into the mixed layer. So this whole idea means that you might have an entrainment of free air up above the interfacial layer down into the mixed layer. Entrainment velocity above, and then you entrain some air, it will it effectively brings momentum down into the layer. It exchanges momentum across that layer. If you have some tracer up here, a tracer jump, delta C like this, and you entrain some air from above, it effectively brings some air into your boundary layer, and so you get like a Reynolds stress style contribution. And you might wonder, how big is this entrainment velocity likely to be? Well, it could be as big as W star if you wanted. If every plume that went upward just gobbled up the air above it, the interface would just move upwards at the rate of a plume ascending. So the entrainment velocity would be given by the convective velocity. But actually, a better way to think about it is, this is the shear production that goes along with that. But remember, there's also this temperature gradient, this capping inversion up above, that's what's really helping set the depth of the mixed layer. So if a plume comes up through the mixed layer and bangs into this warmer air up here, it's going to be not convectively unstable, but it enters a region where it's stably stratified again. And so if you think about it as the Richardson number up in that interfacial layer, how stratified is this layer? Here the temperature's climbing, but we also have some shear that's essentially coming from the turbulence below. You can work out a scaling like this, which you can compare to the Richardson number that you might find for the convective boundary layer itself. So the interfacial layer versus the Richardson number for the convective boundary layer, you take the ratio of these two things and you see that it basically gives you the entrainment velocity over the convective velocity. So within the interfacial layer, you expect a larger Richardson number because it is stably stratified, or at least on its way to becoming stably stratified. In the convective boundary layer, you expect a very, very small Richardson number, 0.2, because it's unstably stratified, it's convecting actively. And so comparing those two Richardson numbers to each other tells you that the entrainment velocity should be smaller than the convective velocity by exactly that ratio of the flux Richardson number for the interfacial layer versus the flux reaches a number for the convective boundary layer. Okay, so that was all I wanted to talk about today. We have so now we've got a sense of what happens in the convective boundary layer. We have a sense of the atmospheric boundary layer as having three important layers. Three potentially important layers. There's always a surface layer. There can be a convective boundary layer on top, or there can be a stable boundary layer on top. And we're going to talk next time about the stable boundary layer. And then on Friday, I want to just talk about questions on the homework for the whole day, which could be questions either from past homeworks or questions for the last homework. Are there any questions right now? So you can't see this, but I'm checking the calendar right now to make sure that I've got the deadlines for everything right. So our plan is that we're going to finish talking about Wyngaard this week, and then it won't be till the end of next week that the homework will be due. So please take a look at the homework before Friday for this last homework assignment, and so that we can discuss it on Friday. Then next week we'll be talking about different closures, different parameterizations, how we think about baroclinicity and boundary layers in the ocean as well as the atmosphere, and how that leads us to think about submesoscales and mesoscales and how they're connected through the boundary layer. All right, if there are no more questions, thanks everyone. I get all the questions in the chat box. Okay, bye-bye everybody.